Using the National Electrical Code Table 310.15b16, the voltage drop for 250 kcmil aluminum XHHW cable in a 4-inch PVC conduit at 200 amps is approximately 2.27% for a 575-foot run. The maximum allowable voltage drop for a branch circuit is 5%. For a 240-volt circuit, this means that the voltage drop should not exceed 12 volts. That is 5% of 240 volts. Based on the calculation, the voltage drop for 250 kcmil aluminum XHHW cable is well within the National Electrical Code limit of 5%. Therefore, it is not overkill. The customer's reluctance to install a primary service may be due to the high cost of the transformer and installation. However, in the long run, primary service can provide better voltage regulation and reduce maintenance costs. The choice of cable size also depends on the anticipated load and future expansion plans. If the customer intends to add significant loads in the future, then a larger cable size may be warranted. Based on the voltage drop calculations and National Electrical Code requirements, 250 kcmil aluminum XHHW cable is an appropriate choice for the 575-foot secondary service. It meets the safety and efficiency requirements. When dealing with electrical installations, it is crucial to adhere to the National Electrical Code, or NEC, which provides guidelines for safe and effective wiring practices. One critical aspect of electrical design is calculating voltage drop, which is the decrease in voltage along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can lead to inefficient operation of electrical equipment, overheating, and even safety hazards. The NEC sets limits on the allowable voltage drop to ensure proper functioning and safety of electrical systems. In the scenario presented, there is a 575-foot underground service consisting of a 200 amps, 120/240 volt single-phase system. The conductor is run in a 4-inch PVC conduit from the transformer to the house, making it a secondary service. The initial plan involves using 250 kcmil aluminum XHHW conductors to address voltage drop concerns. To determine if this conductor size is appropriate, a voltage drop calculation must be performed and compared against NEC requirements. According to NEC Table 310.15b16, the voltage drop for 250 kcmil aluminum XHHW cable in a 4-inch PVC conduit at 200 amps is approximately 2.27% for a 575-foot run. This value is crucial in assessing whether the proposed conductor size meets the NEC voltage drop limits. The NEC specifies that the maximum allowable voltage drop for a branch circuit is 5%. For a 240-volt circuit, this translates to a maximum voltage drop of 12 volts, calculated as 5% of 240 volts. Comparing the calculated voltage drop of 2.27% to the NEC 5% limit, it is evident that the 250 kcmil aluminum XHHW cable falls well within the acceptable range. This indicates that the conductor size is not overkill and is suitable for the intended application. Several factors influence the decision to use a specific conductor size. Firstly, the length of the run plays a significant role. Longer runs result in higher voltage drops due to increased impedance. Secondly, the current flowing through the conductor also affects voltage drop, with higher currents leading to greater voltage drops. Thirdly, the conductor material and size determine its resistance, which directly impacts voltage drop. Aluminum conductors, while more cost-effective than copper, have higher resistance and therefore require larger sizes to achieve the same voltage drop performance. The NEC provides tables and formulas to assist in calculating voltage drop, taking into account these factors. In addition to voltage drop considerations, other factors should be taken into account when selecting a conductor size. These include the anticipated load, future expansion plans, and environmental conditions. If the customer intends to add significant loads in the future, a larger conductor size may be warranted to accommodate the increased current demand. Similarly, if the installation is exposed to harsh environmental conditions such as high temperatures or corrosive substances, a more robust conductor may be necessary to ensure long-term reliability. The customer's reluctance to install a primary service may stem from the higher upfront cost associated with transformers and installation. However, it's important to consider the long-term benefits of primary service, such as improved voltage regulation and reduced maintenance costs. Primary service typically offers better voltage regulation because the transformer is located closer to the load, minimizing voltage drop. Additionally, primary service can reduce maintenance costs by reducing the strain on the distribution system. In conclusion, based on the voltage drop calculations and NEC requirements, the 250 kcmil aluminum XHHW cable is an appropriate choice for the 575-foot secondary service. It meets the safety and efficiency requirements outlined in the NEC and provides adequate capacity for the intended load. However, it is essential to consider future expansion plans and environmental conditions when making the final decision on conductor size. Always consult with a qualified electrician to ensure that the installation complies with all applicable codes and regulations. This will help ensure the safety and reliability of the electrical system for years to come. When dealing with electrical installations, it is crucial to prioritize safety and adhere to established codes and regulations. The NEC serves as a comprehensive guide for electrical wiring practices, providing detailed requirements for conductor sizing, overcurrent protection, grounding, and other essential aspects of electrical systems. By following the NEC, electricians and installers can minimize the risk of electrical hazards and ensure the proper functioning of electrical equipment. In the scenario described, the selection of 250 kcmil aluminum XHHW cable for a 200 amps, 120/240 volts single-phase service is a critical decision that impacts both safety and efficiency. The choice of conductor size must take into account several factors, including voltage drop, ampacity, and environmental conditions. Voltage drop, as previously discussed, refers to the decrease in voltage along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can lead to reduced performance of electrical equipment, overheating, and even premature failure. The NEC sets limits on the allowable voltage drop to ensure that electrical systems operate within acceptable parameters. Ampacity, on the other hand, is the maximum current that a conductor can carry continuously without exceeding its temperature rating. The NEC provides ampacity tables that specify the allowable ampacities for different conductor types and sizes, based on factors such as insulation type, ambient temperature, and installation method. Selecting a conductor with adequate ampacity is essential to prevent overheating and potential fire hazards. Environmental conditions also play a significant role in conductor selection. Factors such as ambient temperature, moisture, and corrosive substances can affect the performance and lifespan of conductors. In harsh environments, it may be necessary to use conductors with special insulation or coatings to protect them from damage. In the case of the 575-foot underground service, the use of 4-inch PVC conduit provides a degree of protection for the conductors against physical damage and environmental factors. However, it is still important to select conductors that are suitable for underground use and are resistant to moisture and corrosion. Aluminum XHHW conductors are commonly used for underground installations due to their durability and resistance to moisture. However, it is essential to ensure that the conductors are properly terminated and sealed to prevent moisture from entering the connections. Proper grounding is another critical aspect of electrical safety. Grounding provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and energize the circuit. The NEC specifies detailed requirements for grounding electrodes, grounding conductors, and bonding of metal enclosures to ensure effective grounding. In the scenario described, the grounding system should be carefully designed and installed to comply with NEC requirements. This may involve the use of ground rods, ground rings, or other grounding electrodes, depending on soil conditions and other factors. Overcurrent protection is also essential to protect conductors and equipment from damage due to overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. The NEC specifies the maximum allowable overcurrent protection for different conductor sizes and types. In the case of the 200 amp service, the overcurrent protection device should be sized appropriately to protect the 250 kcmil aluminum XHHW conductors. It is important to note that the selection and installation of electrical equipment should always be performed by qualified electricians who are familiar with the NEC and local codes. Electrical work can be dangerous if not performed properly, and it is essential to take all necessary precautions to ensure safety. In addition to the technical aspects of electrical installations, it is also important to consider the customer's needs and preferences. In the scenario described, the customer expressed a reluctance to install a primary service due to the higher upfront cost. While this may be a valid concern, it is important to educate the customer about the long-term benefits of primary service, such as improved voltage regulation and reduced maintenance costs. Ultimately, the decision of whether to install a primary or secondary service should be based on a thorough analysis of the customer's needs, budget, and long-term goals. By carefully considering all of these factors, it is possible to design and install an electrical system that is safe, efficient, and meets the customer's needs. Electrical systems are governed by a complex interplay of factors, all of which must be carefully considered to ensure safe, reliable, and efficient installation. Among these considerations, voltage drop, ampacity, grounding, and overcurrent protection stand out as particularly critical. Understanding their principles and adhering to the National Electrical Code, or NEC, guidelines are paramount for any electrical professional. Voltage drop, the reduction in electrical potential along a conductor, can significantly impact the performance of connected equipment. Excessive voltage drop can lead to reduced power output, overheating, and even equipment malfunction. The NEC sets limits on allowable voltage drop to maintain optimal operating conditions. Factors influencing voltage drop include conductor length, current, and conductor material. Longer conductors, higher currents, and materials with higher resistivity contribute to increased voltage drop. Calculating voltage drop accurately is crucial for selecting appropriately sized conductors. Ampacity, the current carrying capacity of a conductor, is another vital consideration. Exceeding a conductor's ampacity can lead to overheating, insulation degradation, and potentially fire hazards. The NEC provides ampacity tables that specify the maximum current a conductor can safely carry based on its size, insulation type, and ambient temperature. These tables must be consulted to ensure that conductors are not overloaded. Grounding, establishing a low impedance path for fault currents, is a fundamental safety measure. A properly grounded system provides a path for fault currents to return to the source, tripping over current protection devices and preventing electrical shock hazards. The NEC outlines detailed requirements for grounding electrodes, grounding conductors, and bonding of metallic components. Overcurrent protection, provided by circuit breakers and fuses, safeguards conductors and equipment from excessive current flow caused by overloads and short circuits. These devices interrupt the circuit when the current exceeds a predetermined level, preventing damage and potential fires. The NEC specifies the maximum allowable overcurrent protection for different conductor sizes and types. In the specific scenario of a 575-foot underground service with a 200 amps, 120/240 volts single-phase supply, several factors come into play. The length of the run necessitates careful consideration of voltage drop. Using 250 kcmil aluminum XHHW conductors mitigates voltage drop concerns, keeping it within the NEC recommended limits. Aluminum, while less conductive than copper, offers a cost-effective solution when appropriately sized. The XHHW insulation provides moisture resistance suitable for underground applications. The 4-inch PVC conduit provides physical protection for the conductors. Proper grounding and overcurrent protection are essential for safety. Grounding electrodes, sized according to the NEC, should be installed to provide a low impedance ground path. A 200 amp circuit breaker or fuse protects the conductors from overloads and short circuits. The customer's reluctance to opt for a primary service highlights the importance of clear communication and education. While a primary service offers advantages such as better voltage regulation and reduced maintenance, the initial cost can be a deterrent. Explaining the long-term benefits and comparing the overall cost of ownership can help the customer make an informed decision. Ultimately, the choice depends on their specific needs and budget. Proper planning, calculation, and adherence to the NEC are crucial for a safe and efficient electrical installation. Consulting with a qualified electrician is always recommended to ensure that all requirements are met. Electrical systems are complex and demand a comprehensive understanding of their principles and regulations. Voltage drop is a critical consideration in electrical installations, especially in long runs. Excessive voltage drop can lead to various problems, including reduced equipment performance, increased energy consumption, and potential damage to electrical components. The National Electrical Code, or NEC, provides guidelines and recommendations for minimizing voltage drop in electrical systems. Several factors contribute to voltage drop, including conductor length, current conductor size, and conductor material. Longer conductor runs, high currents, and smaller conductor sizes generally result in greater voltage drop. Conductor material also plays a significant role, with materials having higher resistivity, such as aluminum, exhibiting greater voltage drop compared to materials with lower resistivity, such as copper. To mitigate voltage drop, it is essential to select appropriate conductor sizes and materials for the specific application. The NEC provides tables and formulas to assist in calculating voltage drop and determining the minimum conductor size required to maintain acceptable voltage levels. In the scenario of a 575-foot underground service with a 200 amps load, voltage drop becomes a significant concern. Using 250 kcmil aluminum XHHW conductors helps to minimize voltage drop due to the larger conductor size and the properties of XHHW insulation. However, it is still necessary to perform voltage drop calculations to ensure that the voltage drop remains within acceptable limits. The NEC recommends that the voltage drop for branch circuits should not exceed 3% and the voltage drop for feeders and services should not exceed 5%. These limits are intended to ensure that electrical equipment operates efficiently and reliably. To calculate voltage drop, several formulas can be used, depending on the type of circuit and the available information. One common formula for calculating voltage drop in single-phase circuits is voltage drop equals 2 times current times length times resistance per unit length, divided by 1000. Where voltage drop is the voltage drop in volts, current is the current flowing through the conductor in amps, length is the length of the conductor in feet, and resistance per unit length is the resistance of the conductor per 1000 feet. The resistance per unit length can be obtained from NEC tables or from conductor manufacturers. Once the voltage drop is calculated, it can be compared to the NEC limits to determine if the conductor size is adequate. If the voltage drop exceeds the NEC limits, a larger conductor size may be required. In addition to conductor size, other factors can also affect voltage drop. These include the type of conduit or raceway used, the spacing between conductors, and the ambient temperature. The NEC provides guidelines for these factors as well. Proper installation practices are also essential to minimize voltage drop. Conductors should be installed in a neat and workmanlike manner, with proper connections and terminations. Loose or corroded connections can increase resistance and contribute to voltage drop. It is also important to ensure that conductors are properly supported and protected from physical damage. In the scenario of the 575-foot underground service, the use of 4-inch PVC conduit provides physical protection for the conductors. However, it is important to ensure that the conduit is properly installed and sealed to prevent moisture from entering. Moisture can corrode conductors and increase resistance, leading to increased voltage drop. The customer's reluctance to install a primary service may be due to the higher upfront costs. However, it is important to consider the long-term benefits of primary service, such as improved voltage regulation and reduced maintenance costs. Primary service typically provides better voltage regulation because the transformer is located closer to the load, minimizing voltage drop. Additionally, primary service can reduce maintenance costs by reducing the strain on the distribution system. Ultimately, the decision of whether to install a primary or secondary service depends on the customer's specific needs and budget. However, it is important to educate the customer about the benefits of primary service and to ensure that the chosen service meets their long-term needs.